Let's get to work now on a capacitor example. In this example, I've got two round electrodes. They're held a half a centimeter apart, so they're forming a capacitor. We connect those the electrodes to the terminals of a 15-volt battery. We want to find something about the charge, the electric field, and the potential difference for some various situations. First, let's just describe our capacitor so we're sure we understand what's happening. So here's a picture of our capacitor. We know that they're round electrodes because the problem gives us a diameter. If the diameter is a half of a centimeter, then the radius is 0.25 centimeters. Oh wait, sorry, I looked at the distance and I said that was the radius. The diameter from here to here is 10 centimeters. So the radius from here to here, I'll call that R, that's 5 centimeters. What happens when we hook up these two metal plates to a battery using a metal wire is that charge starts to flow. By convention, we say that positive charge comes out the positive end, so the current flows up this way. All those positive charges flow until they hit this plate. Once they hit this plate, they can't go anywhere because there's space in between the two plates, so the positive charge is stuck here. There's a net amount of charge Q. And then every positive charge here is going to repel a positive charge from this plate. And those positive charges will move far away from it. They will move back down to go back into the battery. If all of the positive charges are leaving the battery, or leaving the electrode, then that leaves this electrode with a net negative charge. So this plate has charge plus Q, this plate has charge minus Q. Some things that we know is that the charge density on the plates, sigma, is going to be the charge over the area. The area where it's round is just given by pi r squared. Okay, if we have a positive charge here and a negative charge here, we have a charge separation that tells us that there's going to be an electric field between the plates. There will be an electric field that points from one plate to the other. Something like this. The plates are separated by some small distance d. D is equal to 0.5 centimeters. If we have an electric field over a certain distance, then we know that the field and the distance and the potential are all related through E equals delta V over D. The last thing we'll point out is that the charge flows around this circuit and charges up the capacitors until the potential across the capacitor is equal to the potential of the battery. So in general, if our battery had potential given by epsilon, then the charge is going to flow until the potential across the capacitor plates is also epsilon. So that's what happens when we first hook up the battery. Once we get a potential of epsilon across these plates, the charge no longer flows and there's no more current. So I think that's a nice deep description of what's happening with the capacitor. Now let's get into answering the questions. So for part A, while the capacitor is attached to the battery, so in this situation that we drew here, what is the charge on each electrode, what is the electric field strength, and what is the potential difference? Okay, let's start with the potential difference. We said that the capacitor would charge up until the potential difference across the plates was equal to the potential of the battery. So delta V, the potential difference across the plates of the capacitor, is equal to the potential of the battery, which is 15 volts. And we're going to do these questions out of order just because it's a little bit easier. What is the electric field strength? Well, we know that the size of the electric field is the change in potential, delta V, divided by the separation. So we've got 15 volts over the plate separation, we said was a half of a centimeter, 0.005 meters, gives us 3,000 volts per meter. If you were asked for the electric field as a vector, you would specify the direction as from the positive plate to the negative plate. And last, what is the charge on each electron, on each electrode? Well, we know that electric field between the plates of a capacitor is charge density over our constant epsilon naught. The charge density is charge over area. Our electrodes are circular, so our area is pi r squared. We can solve for our charge equals the field times pi r squared times epsilon naught. The numbers we'll plug into this equation are the electric field is 3,000 volts per meter. R is the radius of the plate, which is 5 centimeters, 0.05 meters. Epsilon naught is our permittivity of free space, 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. Put all those numbers into our equation for charge, and what we get is 2.08 times 10 to the minus 10 coulombs. As a bonus question, you could also ask, what is the capacitance? There'd be two ways to find your capacitance. Your capacitance C is given by charge over change in potential difference. We know our charge, we know our potential difference. You can also find it from the geometry of your plates, because we know it's the constant times the area of the plates divided by d. We know the area is pi r squared, d is 5 centimeters. If we put that together, we would get 13.9 times 10 to the minus 12 farads, which we would probably write as 13.9 picofarads. So P for pico, which means times 10 to the minus 12. Okay, there's part A. Now let's move on to part B. For part B now, we use insulating handles to pull the electrodes away from each other until they are 1 centimeter apart. So now what we've done is we've taken our electrodes and we've pulled them, so now we've doubled the separation. D equals 1 centimeter. The electrodes remain connected to the battery during this process. The fact that we're using insulating handles tells us that the plates are not grounded. No charge flows off the plates into your hands. So the charge can't get away, it has to stay on the plates. So if we're still connected to the battery, then the charge across the electrodes, the charge on each electrode, has to remain this. Oh, hang on, sorry, I got scrambled up in the words I was trying to say. I'll start over. If we're still connected to the battery, then the battery is still going to charge the plates of that capacitor to have the same potential as the battery. Okay, we're still connected to the battery, so delta V is still equal to the potential of the battery, which is 15 volts. To find the electric field between the plates, because we get one plate charged to be positive and one charged to be negative, we can find our electric field between the plates as the potential difference between the plates divided by the separation. That gives us an electric field strength of 1500 volts per meter. You might notice that when our plates are twice as far apart, our electric field is half the size. When it's further apart, our electric field gets weaker if the potential difference stays the same. Okay, what else? We'd also like to find the charge. We'll use that same process. E is sigma over epsilon naught. Sigma is Q over A. A is pi r squared. So Q is equal to E times pi r squared epsilon naught. Our electric field is 1500. Epsilon naught is our constant. The radius of the plates did not change. So R is still equal to 5 centimeters or 0.5 meters. That gives us a charge on the plate of 1.04 times 10 to the minus 10 coulombs. So comparing our answers from part A, Our electric field is cut by half when we increase the plate separation, when we double the plate separation. And our charge is decreased by half when we weaken the electric field. So we do get some differences in the problem when we change the geometry of the capacitor plates. Okay, let's do our bonus question. What is the capacitance? You can do C is equal to Q over delta V, or you can do C is equal to epsilon naught times A over D. Whichever one you choose, what you'll get is 6.95 picofarads. So your capacitance cuts by half as well. So if your charge changes and your delta V stays the same, you change your capacitance. There's part B done. For part C, we're going to do a new setup for part C. In part C, we're going back to our original plate separation. D is equal to 0.5 centimeters. But we're changing the radius of the plates. So now they go up to 20 centimeters in diameter, or radius of 10 centimeters. Let's see what happens this time. For what it's worth, I don't actually know how you would expand the plates of a capacitor while it was hooked up to the battery. I don't know, maybe you grab a wooden rolling pin or something. So the potential between the plates of the capacitor is still going to be equal to the potential of the plates of the potential of the battery, because it's still hooked up to the battery. Delta V equals epsilon equals 15 volts. The electric field is going to be delta V over our plate separation D. And for D, we went back to our original plate separation. So we've got 15 volts over 0.005 meters to get 3,000 volts per meter. Okay, so our electric field is exactly the same as what we had in part A, because the electric field depends on the potential, which is the same, and the plate separation is the same. So that electric field is the same as what we had in part A. Okay, next let's find the charge on each plate. Let's just skip right to our expression. The charge is the electric field times pi times r squared times epsilon naught. Our electric field is 3,000. Our r is 10 centimeters, or 0.1 meters. That gives us a charge of 8.34 times 10 to the minus 10 coulombs. Now if we look at the charge, we've doubled our radius and we've increased our charge by a factor of 4. Okay, so when you double the radius, because of the squared sign here, you increase your charge by 4. And then let's finish off by our bonus question of finding our capacitance. C is equal to Q over delta V, or C is equal to epsilon naught A over D. So we see that our R is a factor here. And when we do that calculation, what we get is 55.6 picofarads. And we see, compared to part A, we increase the capacitance by a factor of 4. So if you increase the charge by 4, you increase the capacitance by 4.